In this video, we're going to explore two important reactions of alcohols, one with TsCl, which is one of the short forms you see for para-toluene sulfonyl chloride, a derivative of para-toluene sulfonic acid. Pyridine will be used as a proton scavenger. It will take a proton as soon as it's acidic enough. Right now, there are no protons of that variety. We're making a para-toluene sulfonate ester, where, if you look carefully, this is toluene sulfonate, which is the conjugate base of toluene sulfonic acid, connected to carbon instead of hydrogen, making an ester. What is the synthetic utility of this molecule here, which is the same as this short form? They are both secondary carbons with excellent leaving groups. That means you can use them for SN1, SN2, E1, E2, NGP. Side products. Pyridinium chloride. Pyridine got its proton and became pyridinium. Chloride came from here. Moving down here, a very related reaction with a quite different outcome. Same alcohol. Thionylchloride reacts pyridine, same role. Creates a different secondary carbon with a leaving group. Generates sulfur dioxide gas. Where the second chlorine go is same place the one above went. We need to get busy. The reason we're doing these together is the mechanisms are identical to a certain point. So I'm going to do them both simultaneously. The sulfurs in both examples have multiple bonds to more electronegative atoms, making the sulfurs very positive. This attracts the lone pair on oxygen thus. Lone pair on oxygen goes to the sulfur. What breaks first, a pi or a sigma? Rhetorical question. Pi's are weaker than sigmas. They break first. Same arrows below. If we're lucky, we can just slide them down. Look at that. Okay. We would prefer that arrow going closer to the oxygen and not outer space. What is the result? Well, we're going to generate oxonium ions. These two oxonium ions have pKa's less than 0. Pyridine can now deprotonate them. Before we do that, I don't want to have to keep drawing this over and over again. You can clearly circle it. You have to clearly do this. And say from now on you're going to call that R. And then you don't have to draw it anymore. And we're moving on. Pyridine has a lone pair which can deprotonate the oxonium. We will show that. Lone pair picks up the proton. Sigma bond becomes lone pair. And the exact same thing happens down here. And we generate these intermediates. This intermediate here and this intermediate here. They will undergo what's called an elimination. You know what that means. You're going to make a pi bond. Lone pair comes in and chloride gets kicked off as a leaving group, generating a S-double-O pi bond in both examples. In our first example, it generates your toluene sulfonate ester, and that mechanism's done. Let's account for the fact that during this step we made pyridine into pyridinium. That's accounted for right there, and the chloride came off right here in this last step. So we should put another arrow pointing towards chloride. Once again, on tests, I am not too concerned that you have these last arrows pointing towards side products at all. You can stop your mechanism as soon as you finish this step here. We're not finished down here. In the mechanism above, chloride is a nucleophile that you created, but it's not a good enough nucleophile to do a backside attack on this carbon, on this secondary carbon with a leaving group. Chloride is a little misleading. It's not that great a nucleophile. I put it in the moderate category if you were doing a chapter 9 analysis. You're going to need a better leaving group than an excellent leaving group. Interesting. What's better than excellent? How about exceptional? All right, we do have an exceptional leaving group possibility over here. Backside attack. And this leaving group is not your garden variety leaving group. What happens here is you make a pie, and the chloride leaves, and you generate a couple things. You generate SO2 gas. That is an exceptional leaving group. Being a gas makes it an entropy-driven reaction. And we generate our secondary alkyl halide, and most importantly, the stereocenter is flipped. It's now R, and it used to be S. So in this video, we've accomplished an important objective, taking readily available alcohols to make them into carbons with leaving groups where the stereocenter 1 stays the same or 2 is flipped. Alcohols are very common starting materials for synthesis because they're readily available and usually fairly inexpensive. So there you have it. We have alcohols reacting with toluene sulfonyl chloride and thionyl chloride, giving secondary alkyl halide, secondary alkyl carbons with excellent leaving groups, either a toluene sulfonate ester or an alkyl chloride. I hope you found this video to be helpful, and I look forward to our next video.